Today, we're diving into an absolutely groundbreaking ECCV 2026 paper by Cao Dui and Fengwen Ha that is completely revolutionizing how we generate 3D assets. If you've been following the AI space, you know that taking a simple text prompt or a 2D image and turning it into a fully realized 3D environment is basically the holy grail for developers, roboticists, and graphic artists. But let's be honest, it's also been incredibly frustrating, mostly plagued by agonizingly slow processing times and weird visual glitches. Well, today, we are looking at a brand new framework called PixGS that aims to change all of that.
Now, what if I told you AI could whip up flawless 3D models in just 1 second, completely skipping all those clunky pipelines? That is the exact question we're answering today as we explore a massive leap forward that finally cuts out the frustrating bottlenecks of current 3D generation. Imagine being able to instantly summon high-quality 3D assets without waiting for a massive chain of AI models to slowly crunch the data. That is the promise of PixGS.
Here's our roadmap for today. We'll start with Part 1, the 3D generation bottleneck, move into Part 2, enter PixGS and direct generation, then Part 3, bypassing the latent space. From there, we'll cover Part 4, comprehensive surface supervision, Part 5, the PyTorch implementation, and finally wrap up with Part 6, why this breakthrough actually matters.
All right, let's jump right into Part 1, the 3D generation bottleneck.
Before we get into the weeds, let's make sure we're on the same page about 3D-GS, or 3D Gaussian splatting, since that's the foundational output format we're actually trying to generate here. If you think about traditional 3D graphics, they're usually built from wireframes, hard, rigid triangles. Gaussian splats, on the other hand, are totally different. Think of them more like millions of soft 3D brushstrokes, or tiny glowing orbs of light and color. They overlap and blend seamlessly, which gives you incredibly realistic and mathematically efficient rendering of a scene. But generating these tiny splats directly using AI is notoriously difficult.
And that brings us to the core problem. Right now, models kind of act like a terrible game of telephone. Because there's a scarcity of really high-quality 3D data out there, existing solutions usually try to hack it by adapting large pre-trained text-to-image latent diffusion models. But 2D models don't naturally understand 3D space, do they? So you end up with severe view inconsistencies, like generating a car that looks awesome from the front, but totally warped and melty from the side. To patch this up, developers build these massive, complex cascade pipelines. They compress the data down into a latent space and then decompress it through multiple stages. The catch? That compressed latent space inherently limits the capacity of the model, which leads to decoding artifacts and accumulated errors with every single step of the pipeline.
Which brings us to Part 2, enter PixGS, direct generation.
So instead of hobbling down a bumpy, crumbling staircase of latent compressions, PixGS is more like a perfectly smooth ramp. We are completely replacing those lossy, multi-stage latent pipelines with a highly precise single-stage model that operates directly in pixel space. PixGS bypasses the latent compression entirely. But the truly clever part is that it's designed to still benefit from all the vast generative knowledge those 2D models have already learned. It is literally the best of both worlds. You get the massive knowledge base of existing AI, minus all the artifact-inducing compression.
Let's dig deeper into Part 3, bypassing the latent space.
By directly denoising attributes at every single time step, PixGS pulls off something amazing: precise splat-level regularization. Instead of working with some blurry, compressed approximation of the image, the model is directly tweaking the actual 3D Gaussian attributes, their position, their color, their opacity, right there in the pixel space. Because it's a perfectly pixel-aligned representation, it can finely tune both the visual appearance and the geometry at the exact same time. No tiny crucial details get lost in translation.
Okay, Part 4, comprehensive surface supervision.
You might be wondering, how does it maintain such pristine structural quality without relying on a massive cascade pipeline? Well, it uses a seriously robust supervision strategy. Older methods usually ignore high-frequency structural info, which leaves you with 3D outputs that look smooth, but kind of blobby or featureless. PixGS doesn't do that. It actively supervises the generation process by incorporating surface normals, which control how light bounces off the geometry, along with strict depth mapping. It even throws in advanced metrics like LPIPS for perceptual similarity and log, or the Laplacian of Gaussian, alongside your standard RGB data. Basically, the AI is relentlessly double-checking that every tiny ridge, texture, and structural detail is geometrically flawless from every possible angle.
Moving on to Part 5, the PyTorch implementation.
This is where academic theory meets tangible reality.
We've got a minimal, entirely self-contained PyTorch implementation that is packed with advanced features designed specifically for you to experiment with the core ideas of the paper. Under the hood, the architecture uses a flow matching objective paired with a multi-view diffusion transformer, or DIT, backbone. For the rendering engine, the repo generously provides a pure PyTorch differentiable Gaussian Splat renderer, but, and this is a great addition, it also includes an optional backend for the popular CUDA gsplat library. Add in Plucker ray conditioning for spatial awareness, and you've got a highly sophisticated yet surprisingly compact setup.
And honestly, it is incredibly accessible. You can literally run a smoke test on their synthetic toy dataset today just to see the end-to-end training pipeline in action. The authors included a procedural toy dataset called Toy Blobs. Once you clone the repo, you can trigger a multi-stage training schedule test right from your command line. The system handles all the sampling and the PLI export, and you can instantly view your generated 3D assets dropping right into the out.pixeg's mini folder. It totally bridges the gap between reading a dense computer vision paper and actually running cutting-edge code on your own machine.
Finally, Part 6. Why this breakthrough matters.
So, zooming back out, why is this shift from latent space to pixel space such a big deal for developers and 3D artists? 1 second. That's it. That is the crucial point here, the blazing fast inference speed. PixGS can generate these stunning, high-quality 3D assets in literally just 1 second on a single A100 GPU. By eliminating the multi-stage, computationally expensive pipelines of the past, PixGS vastly outperforms current state-of-the-art multi-stage methods. It offers a robust, efficient, and highly scalable alternative that completely changes the timeline for 3D content generation, whether that's for gaming, graphics, or robotics.
With this robust and efficient open-source powerhouse now freely available in your hands, the only real limit is your imagination.